glad to visit with you today about a couple of areas that we do research in our lab. We're located actually out at the Aerospace Research Center, which is about, I think it's about 10 or 11 miles from campus. It's up in the northwest quadrant of the city. And so students generally who are in the lab, there are probably about 10 faculty and 50 or so students out there with staff. And we, most of the students have their own transportation to get out to the lab from campus, although there is some public transportation, and bikes are always an option in nice weather. But it's a great location. So I'm going to start off with a quiz to see where my audience is with regard to a turbine. So I want you to look at this and tell me, where is the turbine? So I've selected 6 different spots where it could be, and I'll give you a minute to come up with a number. This is a quiz. If you don't pass the quiz, then all right. So the turbine is actually just downstream of the combustor. So if you answered 5 or 6, that is the right answer. And so we're going to talk a little bit about things that happen in what are called the high pressure turbine. That's where the pressure is high, but more importantly, where the temperature is very high and cooling is paramount. And then the low pressure turbine, which is number 6, is the turbine stage that drives high bypass turbofan that drives the fan, which is of course producing 90% of the thrust. So it's a very important from an aerodynamic standpoint. So that's why the name of the lab is the Aerothermodynamics, because we're going to work in both the hot section where we care about cooling, and then in the cold section, colder section where it's aerodynamics. So let's see. So I'm going to talk first a little bit about turbine cooling. So the reason that cooling is so necessary is that historically temperatures have been pushed ever higher in gas turbines to try to pursue higher efficiency. So the efficiency is a direct correlation in a Brayton cycle with the pressure ratio across the compressor. Of course, if you look at like an isentropic compression, as you increase the pressure in the compressor, you also increase the temperature of the gas. So as you drive to higher pressure ratios, you're driving to higher temperatures at the exit of the compressor, which means that in order to produce thrust, you have to add fuel at a higher and higher temperature. And that means it comes out of the combustor very, very hot. And trends over the last 40 years have been to keep pushing that higher and higher. And one of the ways they do that is through very detailed architectures internal to the parts, because we're well ahead of metal temperatures in terms of survivability. They also have ceramic coatings that they put on. And so this study is one where we're looking at innovative ways to cool. And there have been a number of studies that have been looking at different architectures you could use to blow cool air from the compressor internally inside the turbine airfoils and even onto the surface through film cooling. You can see that some of these get pretty complicated, and they're intent on trying to mitigate some aerodynamic effects due to vortex formation. But think about how to manufacture these through a single crystal nickel-based alloy. It'd be very challenging. And so different architectures might be very effective, but they might be something you just can't design through traditional methods of investment casting. So enters direct metal laser sintering. So this is something that you're probably familiar with, sometimes called additive manufacturing. And here, instead of taking a block of metal and cutting out the parts you don't want to get your final product, you start with a bag of powder, and that's a metal powder that can be fused by high energy source like a laser. And so as the laser traverses the powder, it creates a solid material, and you can build that up in layers, which means that you can create some really pretty cool things. You're certainly familiar with this in plastics through rapid prototyping and SLA, but you may not know that this is being done in metals, aluminums, steels, and even high temperature alloys. And this is probably about 5 to 10 years old only. So these parts could survive in a hot section of an engine, and they're seeing inroads into current designs. So we wanted to sort of leverage this DMLS to design something that's we thought would be a good film cooling device. And the device we chose is called a fluidic oscillator. What it does is it naturally is unstable inside those passages, and that instability spreads the fluid, as you can see that's highlighted with a dye there, laterally across the surface. That's exactly what you want to do with cooling, right? You'd like a little teeny hole to cover a wide space. And these are used for other things in flow control and things like that. Even in windshield washers, some of them are designed with these fluidic oscillators. That's sort of what's happening internally from a computational standpoint. So we designed some of these ourselves in plastic and characterized the frequency and their spread angle. And then over the course of about 5 years, myself and some students conducted a very exhaustive test campaign. And this, I'm just sharing this with you, is the kind of thing that would happen in our lab. So we would start with these very large-scale fluidic oscillators that we'd test in our flat plate facility here over on the bottom left. And then when we got to the point where we felt we understood that flow very well, we transitioned those to what we're calling a subsonic nozzle guide vane cascade. This is also in our lab. It has the curvature of an airfoil, turbine airfoil, but it's at low pressure. So and so the Mach number is very low. Then we transitioned that to our transonic nozzle guide vane cascade. So now we're getting very close to the scale of an actual engine size, and we have the correct compressibility or Mach number. And then finally, we tested at the engine scale. And the engine scale, we have the correct Mach number and the correct temperature. So we're actually able to do the whole thing. So this is the final test that we did. We're operating in our facility called the Turbine Reacting Flow Rig. And we have infrared camera that allows us to look at the parts as they were installed in the engine or in this test facility. And then we could run cooling in them. And the students sort of capped their 5-year program. It was funded by the Department of Energy by demonstrating that we did indeed get significant improvements in cooling with this new architecture. So that was kind of a cradle to grave test campaign or research campaign that we conducted that ended last year, and we're continuing some of that in a different venue. So that's a turbine thermodynamics kind of problem. Here's an aerodynamics problem. So I mentioned earlier that the aft end of the gas turbines for high bypass fan is called the low pressure turbine. And this has really long airfoils, slender airfoils, and it's also very heavy. The discs themselves add up to a significant amount of the weight of an engine. And because of how much power is extracted from this flow through the low pressure turbine, even a little bit of efficiency loss makes a huge dent in your overall efficiency. In fact, if you look at what you could do to the specific fuel consumption of an engine by playing around with the component efficiency, you can see that the LPT or low pressure turbine, right, you get twice the bang for your buck there compared to the high pressure turbine. HPC, LPC all of those are a lower return than if you were to adjust or improve the aerodynamics of an LPT. So this is definitely something you'd like to do. And the issue is that there's all kinds of complex flow fields in the turbine because of three-dimensionality of the flow. And there's also, in an effort to extract as much work as possible, very often the flow gets stalled or separated, much like it would stall on a wing, but this is a curved surface, a little bit different type of stall. So this is a very complex flow field, and it's ripe for improvement. We've played around with what's called flow control in this environment, as well as many others. So flow control is where you try to manipulate the flow so it remains attached in this case, or that we clean up these secondary flows. So I'll just go through kind of a breadboard of different ways you can exercise flow control, and then I'll show you some examples. So if you have a boundary layer, and this is, imagine that blue rectangle is the surface of your airfoil where you're trying to extract some work. So you want the flow to be nice and attached to the surface so it doesn't stall. You get really high lift or work or power output. So if the boundary layer looks like this shown, then it's incipient separation and it's probably going to stall. You'd really like to energize that boundary layer by blowing tangential to the surface, so a parallel flow. And what that'll do is it'll add momentum to the flow, and it may not stall. So what was the cost? The cost was blowing through some sort of a slot or something like that. But the win is that that flow over the entire airfoil is now attached, and you can continue to get high work output. You could do this other ways, right? You could imagine if I put a big vacuum pump with teeny little holes on the surface, and they sucked air. Well, they'll suck away this low momentum fluid, and sure enough, that boundary layer will again be attached. This, you might think, why would you want to suck really hot gas, and where are you going to put it? The vacuum's going to melt. But this is used in other environments. Another thing you could do is put streamwise vorticity in the flow. And so one of the things that you're probably familiar with on external aircraft wings, like a civil transport, there are these little metal tabs that stick up from about a centimeter or a centimeter and a half up from the surface. And those are vortex generators. You'll see them in and around the nacelle. And their intent is to mix up the flow and to stabilize that boundary layer. One final way that you could do this is through exciting natural instabilities. And if the flow is rich with instabilities, then you could excite those somehow and destabilize the boundary layer. Similar things could be done with secondary flow management, but let me just talk about this specific case of trying to ameliorate the surface over an airfoil to improve the efficiency, or what we're really going to try to do is we're going to show it in terms of loss reduction. So I have an airfoil here that looks like a low pressure turbine airfoil, and I put in these vortex generating jets. So it's a jet of air that comes in sort of perpendicular to the flow. It creates this nice vortex, and that vortex contributes in this way, right? So it's going to mix up the low momentum boundary fluid and produce some attachment. So we tested some of these, and sure enough, you can see here this blue separation bubble with no control. It kind of goes away when I blow with these steady VGJs way upstream. It's kind of expensive. In other words, it takes a lot of air to do that. So what we found was that you could pulse these jets, right? So if you make them cyclic, then you don't use as much mass flow, and you can still get, this is the loss reduction. So if 1 was the baseline, then a number less than a 1 is a good thing, right? We've reduced the effective loss in this cascade or turbine. We also played around with something called the duty cycle. So the duty cycle would be, this is a 50% on, 50% off pulse. Here's a 30%, 15%, all the way down. We found that really it was pretty incredible reduction in loss by just playing around with different frequencies. So we tried to understand a little bit more of why this happens by looking at some of the dynamics. And so I'm going to show here, this is on a normal sort of an airfoil that you would find on a helicopter rotor or an external wing. So it's no longer a turbine airfoil, but it's the same physics. And I'm going to show the results if you had different pulsing frequencies with the same on time. So these are the pressure coefficient distributions over a wing. So that's basically, you want a high suction peak, right, for this to be nice and stable. The baseline here is completely stalled. You can see that this the CP on the top surface is pretty flat. But if I pulse at 40 hertz, you can see that I'm pulsing fast enough that I keep this low suction peak pretty high throughout. If I wait too long, 20 hertz or even 10 hertz, then there's sort of a phase lag in the response and it wobbles up and down at a much longer period. So you can see that, you know, you can play around with different time constants, and surely in a turbine there'd be plenty of time constants because of the unsteady flows. We've also migrated this to swept wings. So swept wings have a very interesting stall phenomenon where they typically stall out toward the wingtip. You can see that here. And what that does is it creates a pitch instability for the aircraft, right? Because the lift distribution that was going out to the wingtip now is stalled, and that's behind the CG, and so you're going to get sort of a pitch up, you know, without even desiring it, and you may even lose your control surfaces. So this is a bad thing. And one of the ways that's corrected in practice is through something called a passive fence. These are both Russian aircraft, and they've been the primary designers or implementers of things like this. But it's a metal fence that you add to the wing, and it keeps nice control up in your stall. Of course, that's more metal, it's more weight, and also there's drag on that little member, and there's side slip issues. So you'd like to get away from that if you could. So what we've done here is we've played around with something called an active blown slot. So this is the passive slot where it's a metal piece, and here we have a slot where we just blow out of that slot. And I want you to show, this is a tough visualization of what's happening on the wing. So the left one is the baseline, and you'll see it stall pretty badly. And then we have this is going to play again. We have the passive, so that's the metal one, and the yellow line indicates about where that yellow line of the passive fence is. And then the AFC is the active flow control. You can see that the outboard portion actually remains attached. In other words, those little yarns don't go crazy until quite high alpha, high angle of attack. And so this is something that we're playing around with, doing some research on currently for the Department of Defense to see about implementing this in an actual aircraft. So I want to sort of come to the third topic because I'm realizing that I took too long on the first two topics. And we're going to try to leave some time for questions. I think I have 30 minutes overall, do I? Is that correct? Okay. All right. So I got 10 minutes, right? So the last topic is on turbine deposition. You might wonder what's going on with this. Well, so aircraft, you'd love it if they always flew through really clean air, but a lot of times you don't have control over that, or there may be a storm or a volcano or you know, just industrial pollution, right? Fine particulate. If that fine particulate, and you can see from this map that certain regions of the globe have very, very high concentrations of particulate matter in the 2.5 micron range. So this is pretty fine stuff. And flying in those regions means that you're going to have a lot of dirt ingested in your engine that gets collected on surfaces. And why is that bad? Well, it can erode surfaces, which makes them less efficient. It can also clog cooling holes back here in this back section where it was so hot. And that would be bad because it's like plugging up your radiator on your car. Pretty much you're going to be at the side of the road. But in an aircraft, there's no side of the road, so it's could be a really bad situation, right? So we have some facilities, these facilities where we actually can add fine particulate to a hot gas stream and see how it collects on a surface. So this is actually a recording showing some turbine airfoils. These are turbine vanes, and we're going to add some dust right about now. So we add some fine dust. You can see how quickly that accumulates on those surfaces. These are uncooled surfaces, so the temperature is well above the molten temperature of the dust, and it just could really clog up everything on those airfoils, and it looks pretty nasty. So you want to mitigate this, or at least design an airfoil so that the airfoil doesn't lose performance so quickly, right? So these would be sort of dirt-tolerant designs. And we're kind of at the forefront of this technology and have sponsorship from several of the engine companies to look at this phenomenon. So in this case, we have the whole range of, whole gamut of different types of facilities. We have really a flat plate type fundamental test series where we have an impinging jet on a really hot coupon, and we look at how those particles impact. We take high-speed imagery. It's like 40,000 frames per second of fine quartz that's hitting a surface and rebounding, and that helps us understand the mechanics of what occurs. We can also monitor, this is like a millimeter diameter jet that's impinging on a wall. Again, this is high-speed photography with a sort of a microscope or focusing lens. And then we have super high temperature facilities where we can take the temperature to 15, 16, 1700 Kelvin and produce sort of deposits that might appear in an engine at these same temperatures. Because the goal is not just to test and find out what conditions create bad deposits, we also have a lot of modeling going on in our lab where we're trying to predict what would happen if you fly through a certain environment and how quickly things will become untenable, maybe even catastrophic for the engine. So these are just some simulations. This is one where we're actually monitoring particles as they move through a time-accurate solution. So this is the rotor moving relative to the stator. And you can see these small particles kind of follow that flow. If you put large particles in that same flow field, you notice now that they're very ballistic, right? So they're sort of bouncing off the surface and coming back. And that means they have a different trajectory, and they also hit the surface differently. And they may be more or less molten depending on the size as well. We're looking at different ways we can account for the buildup on the surface. So this is a simulation where we have a particle flowing through this jet onto the surface, and it creates these mounds of, that we saw before. And in this case, this is the experimental progression. And this is the computation that we've derived to try to model that. And I'll just point out that this is what you get if you don't account for what's called mesh morphing. So as a surface accumulates a deposit, well, then it has a first order effect on the flow field. And you have to account for that by adapting the grid. And if you don't adapt the grid, look how tall these cones are. So the prediction would tell you that you get 7 times or 6 times the height of that cone compared to what's seen experimentally, 1.6 millimeters, if you don't account for what's called mesh morphing. So we're getting higher and higher fidelity in our simulations. So this is a very active area for us. We have government as well as industry funding, and we're probably looking for at least another student in the fall to be involved in that work. So it's 25 minutes down. You've been very attentive, and I think I'm going to stop sharing so that I can say hello. Let's see if I can. There we go.
We had 2 questions that came in for you. Actually, another one just came in. First one is, does additive manufacturing allow single crystallization?
You know, that's a great question, and I'm not a metallurgist. I would guess not, but don't quote me on that. Just in case you're not, probably the person who asked the question is familiar with what a single crystal is, but just in case they weren't, or others aren't. So when you would typically make these turbine airfoils through an investment casting procedure where you make a mold that's the sort of the negative of that blade, and then you would pour molten metal into it, right? And then you would let that cure, and then you crack off the ceramic mold, and there you have your part. Well, it turns out that if you, instead of allowing that to cool universally, if you cool it directionally, you can actually align all the crystals so that they go in the radial direction. And that makes for the strongest part per weight for a rotating piece of equipment. So that's what single crystal is. You align the crystals in the direction of the radius of rotation. And honestly, I don't know whether DMLS allows you to do that.
So next question, what types of software do you use for modeling?
So we generally use commercial software that's available. ANSYS has a nice fluids package that's used to be called Fluent, but it's ANSYS Fluent now. And then we also have another package that's by Siemens. It's called Star CCM. We use both those.
All right. We have a question. Do you have a preference for aerospace undergraduates or ME students that are undergraduates on who you'd like to work with?
I have a preference for hardworking undergraduates. No, so we have pretty high standards in our lab. So all the students are expected to do both experiments and computational work, because that duality really allows them to I think better understand and straddle the two disciplines. And we also strongly encourage publication. So like to have students very directed and being focused. We have both mechanical and aerospace students in the lab. Actually, I teach in the aerospace curriculum, but about half my students are mechanical engineering graduate students, and I play no favorites. So.
Final question, how have you validated your simulations?
Oh, excellent. Yeah, so the simulations are at several different levels. So, well, so the simulations in the deposition world, we have our own high-speed imagery of particles rebounding off surfaces and sticking to surfaces. So that's what we use there. And then for the flow control and the computational work, we'll do a breadboard experiment where we are able to look with infrared and get surface temperatures, and we compare that to our experimental results, as well as the loss profiles and secondary flows. We can make measurements in our lab with multi-component lasers to get the different components of velocity.